Hi everyone, my name is Joe Barnard and welcome back to Landing Model Rockets. This is episode 4, and in today's episode we're going to design the schematic for the Blip and Blop flight computers. And before we do that, I should probably ask, hey Alexa, how do I design a schematic for a computer?
This joke wasn't funny the first time you told it, and it's not funny now. Just cut to the intro and leave me out of this.
Oh, okay, well, let's get started. Alright, so before we get started, let's do a little recap. We're going to be building 2 different flight computers for our landing model rocket here. One will be called Blip, and one will be called Blop. Blip is the computer that uses mostly breakout board components. It's going to be really easy for most people to solder if they don't have a ton of experience. And then Blop is a lower cost and lower mass version of Blip, so it's all around the better computer, but it will be harder to build. Now, both of these computers are going to work exactly the same way, so if you want to use code for Blip and then advance to Blop, you can do that. We've already come up with a list of capabilities that these computers need to have, and then a rough part list that they'll use to accomplish that. Now, I say rough because I actually did change one big thing since the last video where I claimed that we were going to be using the Atmega 328 processor. That's no longer true. I've switched it to a much more powerful processor called, and I have to read it because it's so long, the MK20DX256VLH7. This is a super powerful processor. It operates nominally at about 72 megahertz, but you can overclock it a little bit, and it might be more familiarly known as the processor that's on the Teensy 3.2 microcontroller from PJRC. Paul Stoffergen from PJRC has put in a ton of work into making these awesome development boards that are Arduino compatible. They're super powerful. They're just all around great solutions. So in keeping with our Blip and Blop requirements, we can either buy these boards directly from PJRC, or we can use the schematics that have been generously published by that company and put that directly onto our PCB for the Blop board. That's the more complicated one. So with that covered, the other thing that I wanted to mention is that this video isn't meant to be a full-on tutorial for PCB design, but it's also not meant for just entertainment. I'm trying to find some interesting middle ground where we can get not too bogged down into the details, but cover most of the important parts. If this is your first time designing a printed circuit board along with this series, first of all, that's awesome, and second of all, you may want to check out an actual full-fledged tutorial before you view this video. I'm also by no means an expert here. I learned through YouTube tutorials as well, so I'm going to link a couple of my favorites down below, and you can check them out if you want to get into it. But with all that said, let's get started. Okay, so to get started here, we're going to go ahead and open up Eagle, which is our schematic design program. So here's the little terminal that it comes up with. We're going to go ahead and click File, New Project, and we're going to call this Blip Blop. Oops, Blip Blop. There we go. Now in that project, we're going to create a new schematic. And here we go. So this is our schematic. If you're using Eagle for the first time, this might be a white color, but I changed my background to black because I think the contrast looks a little nicer. It's a little easier on the eyes too. Okay, so let's get started. We need to add some parts. If you're not already familiar, PCB design basically happens in 2 parts. You have the schematic and then you have the layout. So we're starting with the schematic, and that's sort of an abstract representation of what electrical connections need to happen on the board. And then the layout, which we'll do later, is the actual physical placement of the components on the board and then the routing of the little copper traces. So, like I said, we're going to start with the schematic. So we've got our empty schematic file here, and we need to add some parts. So I'll click this button, and what you'll notice is that there are already a ton of available parts that we can use for our design. These are parts that come with Eagle, or these are libraries that are available for download online. Now, if you remember in the last video, we spec'd around parts that are existing and have good support online. And one of the benefits here is that if these parts aren't available in the existing Eagle libraries, we can just go to the internet and find them and then put them in our project. So we'll start off with our processor here, and that's the Teensy 3.2 like I mentioned earlier. So if I type in Teensy into the search bar, I'll find that I have all of these boards already downloaded and in my library that I could put into my schematic file. But let's say that you didn't already have these, like you hadn't done any PCB project before. So what you could do here is go to Google and type in Teensy 3.2 Eagle. Oh look, I've already typed it in before because I had to do multiple takes of this part. But here we go. We'll go here and look at the PJRC website where there are actually files that you can just directly drop into your project. So this is super helpful if you don't have a part already existing. So I'll close this. I'm gonna go ahead and pick out, let's see, I think this is the one we want here. So this is the component that we want right here, teensy 3.1 or 3.2 and outer row only. We don't need these sort of inner components that are in there. So let's go ahead and pick this out. I'm gonna click OK, and then drop it into the schematic. All right, now we need some other components here, so let's start with some of the sensors. We'll start with the IMU, and that is the MPU 6050, if we remember correctly. And look, I didn't type it right. MPU 6050. And nothing really comes up, so I'm wondering maybe I typed something wrong. So here we go, MPU 6000 and MPU 9250. But the problem with these, if you notice the landing pads here, is that these are for just the individual sensors, and we want the actual breakout board, which is sometimes referred to as the GY521. But if I do a search, I'll find that it's just not in my library, and I don't have to search too far because I know it's not in there. I planned this video. So we have to go find this library online. So once again, I'm gonna go to Google and I'm gonna type in GY521 Eagle Library. Here we go. Oh, look, I'll do this. So here we go. It's the GY521.lbr. Looks like someone named Cooked made it. Thank you, Cooked. So I'll go ahead and download this file. Now, I got all these boards, but I only need the GY521, so I'm going to take this file and I'm going to drag it into my Eagle Libraries folder, and then I'm going to go over here into Libraries, and look, there it is, GY521. So I'll expand it a little bit. Here's our part, and this looks like the board that we want. This is the breakout board that we're going to be using. I'm going to take this, and I'm literally going to drag it into our schematic. So 1, 2, 3, boom. Now, let's find our barometer. Okay, so we'll go ahead and do the same thing for the BMP280, and you can see I've already typed it in again. We'll go ahead and look it up, and what we find is that most of these files are actually for either a different breakout board, one that doesn't match our pinout, or it's for the actual board design file itself, which again, we don't actually want. So the good news is it would be really easy for us to actually build our own library for this thing. So let's get a little experience and do that. Back in Eagle, I'm gonna go ahead and say File, New, and Library. So we're gonna make a new library here, and within that library, we're gonna make a new symbol. This stuff might seem super confusing at first, but I promise it'll make sense as we go along. So I'm gonna go ahead and say BMP280, enter, create new symbol. And then the symbol is basically, if you look over to the right here, this is a symbol for the GY521 board, and over here is our symbol for the Teensy 3.1 or 3.2. So what we're creating is this little red outline of the board. This is where we're going to actually draw our connections. It doesn't have to represent a super accurate representation of the actual physical board. It just has to show the connections. So I'm gonna go ahead and draw some lines here. We're just gonna draw a little box, and we're gonna call this, hold on one sec. There we go, draw a little box, boom. Now we're gonna make some connections. Once again, I just wanna let you know this is not a full-fledged tutorial. If you're confused about what's going on, there are lots of tutorials linked in the description that will explain this a little bit more clearly. So I'm gonna make a couple connections here, and before I do, I'm gonna go ahead and look up the BMP280 again, and really what I wanna see is just all of the different connections in the photo of this board. So I'm gonna go ahead and replicate those here. How many do we have? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is not perfect, but it's pretty close. Now we need to go ahead and name these little connections. So let's do that. This one, if we look over here, this one's VIN. That's the voltage input. So we're just gonna name them identically. VIN, and we're gonna name this one 3VO, which is a 3-volt output. We don't need that. For our computer at least. GND, that's ground. Then we're gonna say SCK, SDL, SDO, SDI, and CS. All right, and to round it out here, we're gonna go ahead and name this thing the BMP280, because that's the sensor name. Gonna make this text just a little bit larger. There we go, BMP280. And that looks good to me. So this is our symbol for the device. Now we need to make a footprint, and this is the physical representation of the device. So once again, BMP280, enter, create new footprint, and we're at this page. Okay, so now this is the physical representation of this device. So I need to get some measurements on how big this thing is. Let's go back to Adafruit and look for some documents under technical details. Now there are a bunch of files here that we can use, and they even provide their own PCB files on their GitHub. So what we're gonna do is we're gonna just download these, And I'm going to open up the board now. And so this is the board that Adafruit actually makes, and this is the schematic. Again, it's crazy that they provide all of these files. It's super generous, and again, it just like really represents the maker community and the spirit of it. So I'm going to go ahead and take just a couple of measurements here. I'm going to convert to millimeters because metric is the only way. So if I've moved my mouse over here, the board is roughly 18 by 19 millimeters. So we're going to go back into our library and create a line under the T-place thing that is 18 by 19 millimeters. So we're going to go here, and we're going to go all the way to 18, up to 19, over here to 0, and then back to 0. So this is our outline that's going to be on the PCB. So I'm going to go ahead and just place some holes for the actual part to sit in here. So we're going to go 1, 2, 3, 4, 5, 6, 7. I've got all my spacing set up, so this should be correct as well. And we have to name those holes. So let's go back to this, and they have to match what the actual part is, which is right below. So here we go, VIN. We've got 3VO. We've got GND, SCK, SDO, SDI, and finally CS. So these are our 7 pins here. The other thing we might want to do here is take a page out of the book of Adafruit and label these pins. So let's go ahead and grab our text editor and say VIN, because this is what's going to actually show up on the board. So VIN, the next one's going to be 3VO. Then we have GND. We've got SCK, SDO, SDI, and once again, CS. So here we go, and then one final label here. We're just going to call this the BMP280. We're going to do that. We're going to make the text size just a little bit bigger and put it right there so that when we put things on the board, we know that the BMP280 goes here. So this is sort of our footprint for the board. I'm going to go ahead and create one more thing here, and if you're not following along, just hold out a little bit longer because it's almost over. BMP280, and the device, what this is going to do is it's going to connect together the symbol and the footprint that we just made. So let's go ahead, and where do I click here? I'm going to go add part, the BMP280. So this is our symbol, and then over in this section I'm going to say new, add local package, BMP280, and then I'm going to connect all of these leads between the two. Usually Eagle will get this part right, so all I have to do is say connect, connect. I'm looking for consistency between this column and this column. So here we go, connect, connect, connect. As long as all of these things are the same, connect, done, and that is it. So I'm gonna go ahead and save this as the BMP280, and we are done. We have our BMP280 labeled as a custom part in our library. So like, what does this all mean, Joe? Why did you spend so much time doing this? Well, let me show you. I'm gonna go ahead and open up Blop because it got closed again. So here we go. And now that we've created our BMP280 library, we can see our device right here. So I'm going to go ahead and just drag and drop. And there it is. It's the BMP280. Boom. That is excellent. So we have a barometer, we have an IMU, we have a processor. What else do we need? Well, the next thing is that we need an SD card holder and a flash chip. But I already know that I don't have the libraries for these items, so I'm going to have to make them myself again. I'm going to go through the same process that I did for the BMP280, but I'm not going to show it because I don't want this video to be a billion hours long. So 3, 2, 1, and there we go. We've got our SD card holder and we've got our flash chip. It's crazy how they just sort of appeared like that, but I guess, you know, really do be like that sometimes. Real quick, one thing you might notice is that the flash chip says W25Q32FV. This is not the exact flash chip we're going to be using. It's going to be a slightly different one, and there will be a parts list down in the description below. But this is the same exact pinout, and it's the same exact footprint as the one we're going to be using because a lot of these are very standard size flash chips, so it doesn't really matter that it says the wrong name on there. Alright, so we have most of the core components for our flight computer in our schematic, but we need to add a few more things before we get to hooking everything together. Those things are the LED, the buzzer, we need to add some terminal blocks, and we need to add the MOSFETs that feed them. These are the Pyro channels, basically. We need to add a voltage regulator, and we should add some passive resistors and capacitors to the board as well. So let's get to work on those. The LED is going to be a standard tricolor LED from Adafruit, so I'll go ahead and look that up now. Adafruit tricolor LED. There aren't a whole lot of options here, so it's pretty easy to just find the right one. Here we go, diffused RGB tricolor, common anode. Now I already have a bunch of components and libraries on my computer, so I'm just gonna search for what's existing here. So the name is diffused RGB, so I'm gonna go ahead and search for diffused And you'll see that this is under SparkFun LED, but see this one says CA and this one says CC. We want CA because we want common anode. That's a common anode for the LED. So I'm going to select CA, and this one looks pretty good. This is a diffused LED, diffused LED. I'm going to put this in here. It's SparkFun, but they are basically the same LED. All right, so what else do we need? We need a buzzer. So I'm just going to search for a buzzer here, and I'm going to select their standard 5-volt buzzer, which is also friendly for 3 volts. And it's Adafruit, so it's probably going to exist in my existing parts here as well. I'm going to go buzzer, and under Adafruit, we're going to see that doesn't look like it, that doesn't look like it, neither does that. But under SparkFun, I bet we can find one. This is a 5-volt buzzer. What's the size? Here we go, 6 millimeters long, 12 millimeter diameter. So if we can find another one that's 12 millimeters in diameter, it's probably going to be what we want here. 12 millimeter buzzer PTH, 2 kilohertz. Is this 2 kilohertz as well? Yeah, 2 kilohertz. Beep. Okay, great. So basically what I'm doing here is I'm pulling a lot from the SparkFun guide, but the SparkFun and Adafruit components are nearly identical because they're sourcing from a lot of the same manufacturers. If this is boring, I am sorry. Here we go. We're going to put the buzzer in here, so that should work for us. What else do we need? Some terminal blocks, right? Now, I've already made my own library for these terminal blocks, so I'm going to go ahead and select that here. It's called Black Term Block. Just going to drag and drop, and here we go. So we need 1, 2, 3, 4 for all 4 Pyro channels. And then we need 1 for the battery input, and I think we're going to need 1 for a switch as well. And of course, if we need more, we can just add more later. So what else? What's next? I have a MOSFET. We need some MOSFETs in here. Now the MOSFETs we need, we're just going to search for here, MOSFET and channel power MOSFET. These are way more capable than we actually need for the Pyro channels, but it'll be great. They'll just be super overkill. So this is an Adafruit product, which means I can probably find it in this library again. So let's look up MOSFET. And bingo. Yes, bingo. Okay, here we go. See how it says T0220V, and that is the same package, T0220. So this is the same package as before. These are the MOSFETs we're going to use. I'm going to put 1, 2, 3, and 4. This is what's going to switch our power onto each Pyro channel. And then let's talk about the actual power on the board. Okay, so for voltage regulation on the actual board, we're going to use the 7805. That's a 5-volt regulator. It is pretty common in the hobby and maker industry. So that's this guy right here. Okay, so we've got our voltage regulator here, and I mentioned one more thing, which is the passive resistors and capacitors that need to go on the board. Now, there are a bunch of these, but we're just gonna drop a couple in and then we can copy and paste as we need to. It also doesn't matter what value they have because we're gonna end up changing the value later. So I'm gonna pull a couple of these here. They're gonna be these standard axial resistors. Let me drop these in place. 1, 2, okay, and then we need some capacitors, so I'm gonna go into here and I'm gonna search for capacitor, and here we go. We've got a ton of selection for different types of capacitors. We'll choose something generic like, I don't know, how about 22 PF? All we need is, 2.54. This is a pretty standard size for most capacitors. 2.54 is like a standard 0.1 inch spacing. So we're gonna drop a bunch of these in here. I don't know, how about like 1, 2, 3, 4. Okay, so we have like a decent outline of the components that we're gonna need on this board, and now it's time to start drawing some connections, and we'll get to cleaning some of these things up along the way. All right, so to get started routing everything together, we're gonna do a little power management on this board. So let's zoom in on one of these terminal blocks. We're just gonna push this one out of the way, and we're gonna call this the power input for our computer. Now, I'm gonna click this. This thing is called a net over here, and I'm gonna use this little guy to draw a line out of the out part of this terminal block and out of the in part of this terminal block. So now we've got 2 little connections to this block. Now, I'm gonna put labels on these. One thing that's important to note here, this terminal block says out and in on it, but that doesn't actually matter. It doesn't represent anything. It just means that these are the connections on the terminal block. You can put an input on the out port, you could put an output on the in port. It doesn't matter. I'm gonna call this one BAT plus, and I'm gonna call this one GND, which stands for ground. And all of the grounds are going to be connected to this same GND net, but we're gonna look at that a little bit later. Okay, so we have this other terminal block here, and I'm gonna put it right below the battery one. I'm gonna draw 2 leads from it, 1 and 2. NS2, and this one's actually going to be a switch port. So this one's going to connect the BAT plus to the actual positive voltage that goes into the voltage regulator. Now this is going to make a little bit more sense in a few minutes, but basically what we're doing is I'm adding the option for anyone who's using this computer to add their own switch that could be embedded in the rocket's airframe. It could be a different type of switch, it could be a magnetic one, whatever. It's basically going to allow for a lot more flexibility down the road. So I'm going to add BAT plus to this one, and it's going to say connect NS1 and BAT plus. I'm going to say yes. And now what I've just done is this green line and this green line are now connected. They now represent the same electrical signal. And this one is going to be, what should I call this one? I'm going to call this 12 volts because that's probably the voltage we're going to use from these LiPo batteries or lithium polymer batteries. So we have 3 different nets here. 2 of these are actually connected. And now let's go into a little bit of power management down by this voltage regulator here. First, I'm just going to move this up near the battery so it makes a little bit more sense down the road. And I'm also going to bring 2 of these 22 picofarad capacitors up to the voltage regulator here, and we're going to change the value of these. One of them is going to be 1 UF, or 1 microfarad, and then the other one is going to be 10 UF, or 10 microfarads. And these little capacitors here are basically going to act as some stabilization and filtering of the electrical signals that are coming from the battery and that are coming out of this voltage regulator. It's going to keep our DC voltage just very smooth. All right, so before we do this, I'm actually going to change one thing. I'm going to add one more part to our schematic. I'm going to go here, and I'm going to look up GND, ground. Now, so SparkFun provides some power symbols that just make the schematic look a little bit cleaner. So this little symbol here basically represents a net. So if I connect GND to GND there, that's now a ground net. And any other place that I take this GND symbol and put it, all of these little GND symbols are going to connect. So I'm actually going to redo the nets on this guy right here. Going to go ahead and delete this. And then I'm going to connect it up to ground. Boom. So you'll see we have these 2 ground symbols, and this guy and this guy are now connected. I'm actually going to connect the bottom of these caps to ground because that's where they need to go. Then I'm going to connect the top to the voltage input and the voltage output. So right now our voltage regulator isn't doing anything, it's just connected to ground, so it's pretty much useless. So what I can do here, I'm going to connect the voltage in. If we go back down here, you'll remember I labeled this as 12 volts, and so 12 volts is what's going into the voltage regulator. So let me put a little label on there. And I'm just going to say, we're going to name this 12 volts. It's going to ask me if I want to connect $1 to 12 volts, and I'm going to say yes. So now, let's look. This thing that's coming out of the switch port and going into the voltage regulator, these 2 lines, even though they don't look like it, they are connected. So I'm going to just shorten that to make it a little bit cleaner. And I'm also going to add one more power symbol here, and this one is going to be 5 volts. SparkFun has a bunch of these power symbols, and it's kind of helpful to just keep your, there it is. It's kind of helpful to just keep your schematic looking a little bit nicer. So we're going to add that, connect this up to this, and merge NS2 into supply net 5 volts. Yes. Blammo. We have our voltage regulation. Okay, so what's next now? We have a bunch of other things to hook up, so let's get started with some of the core sensors. This is things like the IMU and the barometer. I'm going to go ahead and clean things up a little bit. Move this guy down here and this guy down here. I'm going to tilt the IMU this way, just like kind of making sure everything looks nice and pretty. So let's start wiring things from the processor. Oh, I know what we can do. We can connect a couple of voltage things up to the processor so that it has power. Let's go over here. I'm going to click copy. We're going to copy this 5 volt symbol, bring it on down to the VIN port on the processor, and 1, 2, 3. Now our processor has power, and we're going to do the same thing with the ground. I'm going to copy the ground symbol from over here. I'm going to put it on the GND part of the processor, and look at that. Now our processor can turn on. Let's connect some things to these sensors. So the BMP280 and the GY521 or the MPU6050, there are so many letters and numbers. Basically, the IMU and the barometer both communicate with the processor over a protocol called I2C or I2C. And it's basically, it uses two different lines to communicate with a bunch of different sensors on that same bus. We won't get into exactly how it works, but that's sort of a general overview of it. So these two different lines are called SDA and SCL. So I'm actually going to tilt this over so it's a little bit easier to work with. I'm going to put this here, going to put this here, and we'll start with the IMU. So SDA, oops, didn't connect that, SDA, and where is SCL? There it is. So I'm going to go ahead and label these guys. And where's our naming tool? Okay, so this one's SCL, SCL, and SDA. So excellent. Now our processor has SCL, and SDA ports on it too, so we're going to break those out. And it looks like we've got SDA0, and make sure that's the right one. Yeah, that's correct. So we're going to break these guys out on 19 and 18, 1 and 2, and we'll put these labels on there as well. And we'll name them. Here we go. SDA. You hear the plane in the background? I live kind of near the airport. Okay, and SCL. There. So now they're connected. You'll see we got that notification again that says, do you want to connect this net to SDA or SCL? And that's because we've already labeled them there. So now, once again, these green lines here and these green lines here are actually connected. Okay, so our inertial measurement unit still needs some power, and it can use either 3 volts or 5 volts. So we're just going to simplify our lives a little bit here and use 5 volts. So once again, I'm going to take the copy tool, copy this 5 volt symbol, and I'm going to put it up here. I'll put it like right there. And then I'll take the ground symbol, and I'm going to put it right here. And bada bing, bada boom, we now have an inertial measurement unit connected to our processor, both of which are powered, which is pretty cool. Now we need to hook up our barometer. That's the BMP280 right here. Now you'll notice that this doesn't have an SCL or SDA port on it, and that's because they're just labeled differently. It can actually do I2C, but it is set up and labeled to use SPI, which is a serial peripheral interface, and it's something that we'll get into just a little bit later in this video. So first, stick around and let's look up the BMP280. We've got a tutorial from Adafruit here. Once again, this is just like absolutely the best thing about speccing around existing components. Adafruit has these great tutorials on like how to use their sensors. So the SPI logic pins, we don't actually want. We want the I2C logic pins because that's how we're going to communicate with this. So SCK, this is also the I2C clock pin, which is SCL. So SCK actually represents SCL, which is crazy. There are so many letters and numbers. Once again, if you're still sticking with it, I mean, you're really a trooper. So we're just gonna pretend that this is SCL, and I'm going to label it here, SCL. That's serial clock. Look, and here we go. We get that notification. Do you want to connect these? And I totally do. So this and this are now connected because SCK is actually SCL. All right, then SDI is the data pin, which is SDA. If you're following along, I really can't believe this. Here we go, we're almost there, and SCL, SDA. Boom, now they are connected. So now the I2C is hooked up to this as well. And if you remember, like last time, we need to give it some power. So I'm going to use the copy tool, VCC. I'm going to bring this up to VIN, and then I'm going to bring the ground. And I'm going to connect that, and boom. Okay, so now we have a barometer and an IMU connected. We're really cruising now. So we used I2C or I2C to connect to the IMU and the barometer. That's the MPU 6050 and the BMP280. But we need a different communication protocol to talk to the SD card and the flash chip, and that's called SPI, or Serial Peripheral Interface. Now, SPI uses a few more lines than I2C does. It uses 3 regular lines to communicate to all of the things on that bus, and then 1 extra line per item on the bus. And this is called a chip select line, or a CS line. So we need 1 extra GPIO pin on the processor to communicate to each thing on our SPI bus. Now, this will make sense more in a second. So let's start by thinking about which things have to come out of the processor for SPI. We have one thing that's MOSI, and that stands for master out, slave in. We have one thing that's called MISO, and MISO out is master in, slave out. So these are not unidirectional, how do you want to say? Just like one direction lines. There's only one direction of communication that can happen on each line. So master out, slave in, master in, slave out. And then we have SCK, which is serial clock. That's just the clock line. And then we're going to need some custom pins for the CS or chip select lines, and that's going to tell the device that is on the SPI line that it's time to listen to the SPI bus. Anyway, I don't know. I'm not here to talk to you about how SPI works. I'm here to wire up flight computers, so let's do that. So I broke out these lines, MOSI, MISO, and SCK. I'm going to label them 1, 2, 3, and then I'm going to name them so that we have the right nets here, MOSI, and then MISO, and SCK. Excellent. Now we're going to connect these to the correct parts here. We're going to start with the SD card holder. So we have DO, which is digital out. We're going to break that out. We have to break out DI, break out CLK, and then break out CS, which is the chip select. Okay, so CLK is obviously going to go to SCK on the SPI bus line. So here we go, SCK, connect NS3 and SCK. We want to do that. So DO. All right, so let's think about this for a second. For digital out of the SD card holder, we want it to go into the master input, which is MISO, master in, slave out. So DO is digital out, so we're gonna go MISO. There we go. And then for digital in, for digital in to the SD card holder, we need master out, slave in, which is MOSI. Okay, if this sounds like gibberish, it honestly is. And then we're going to name this, let's see, SD-CS, which is just going to be the chip select for the SD card. Okay, so next up we're going to focus on the flash chip. So let's break out a couple of these leads. We've got our chip select. We've got our VCC, which is actually going to be connected to 3 volts because this chip operates at 3 volts and not 5 volts. So the good news here is that we have a couple of 3-volt regulators already on this board, and one of them just exists on the Teensy computer. So let's break out this thing. This is the 3.3 volt output of the Teensy. It has a little bit of current that it can provide, so let's break this out. We're going to name this net 3.3 volts. And then in the VCC here, we're going to break out this again. We're going to label it, and surprise, surprise, we're going to call this 3.3 volts, and boom, now our flash chip has power. We need some ground for that too. So let's go ahead and copy this ground symbol right there. We're going to bring it down here and connect it up. Now, this is not a breakout board. This is a standalone flash chip, and there are benefits to this and there are drawbacks. The drawbacks here is that a breakout board will usually have some of the associated passive components that usually have to go with these items. So like, for instance, the IMU has a couple of resistors and capacitors on it. The same with the barometer, same with the processor, all of these things. The good news here is that most of this is pretty easy. So what we're gonna do is we're gonna pull one of these resistors from over here. We're just gonna copy it and we're gonna put it right there. I'm gonna go ahead and break out pin number 7. This is just a hold pin that needs to be pulled up to 3.3 volts. So I'm gonna extend that and boom, now that pin is pulled up. Now we're gonna break out the SCK line, that's the serial clock again, and then we're going to break out the SI line, that's slave in or master out. We're also going to break out the SO line, which is slave out, and we need to get that ground symbol again. I deleted that before, so let's get that. Bring it down here, connect that to ground, and boom. Now there's one more thing that we want to add here, which is a small capacitor, and this is another one of those components that usually would exist on a breakout board, but because we're not using one, we have to sort of do it ourselves. So I'm going to put a capacitor here. It's going to be connected from 3.3 volts on this device to ground. And this is just another little filtering capacitor. So any spikes or shocks in the voltage for this little component are going to be absorbed by this capacitor. So we're going to copy the ground symbol here, and we're going to rotate it, and I'm going to connect it up here. Okay, so now let's label some of these nets that I've created. 1, 2, 3, 4. So first let's do the CS. This is pretty easy. This is the chip select, just like we saw on the SD card. So instead of SDCS, which is what we called that one, this is the individual pin that's going to tell the processor, or sorry, it's going to tell the device that it's time to listen to the serial peripheral interface lines. And so we're going to call this flash CS. The SO stands for slave out, which would go to the master in, which is MISO. That's master in, slave out, so MISO. I'm gonna connect those nets. SCK is just SCK. And finally, the SI is slave in, which goes to MOC, which is master out, slave in. There we go, connect them, and now our flash chip is connected. I just actually realized we forgot to connect the power to the SD card holder, so let's do that too. I'm gonna grab the 5-volt pin right here, put it to 5 volts, grab the ground, put it to ground, and there we go. Okay, so the SD card is now connected as well. So look at this, we've got a bunch of different peripherals connected. We've got our barometer, we've got our IMU, we have our SD card holder, we have our flash chip. So we're making great progress here. So I think next up, let's do the LED. So before we hook the LED up, we should do a little recap. LED stands for light emitting diode, which means these things are diodes. There are actually 3 of them in this one little device because it's a tricolor LED. We have a red, a green, and a blue, and we can make a bunch of different colors with them. So they usually have a specified voltage that they are supposed to operate at, and that voltage usually differs from the logic level or the nominal voltage of the processor. And the other thing is that diodes usually have a very low internal resistance, so they can pull a lot of current and then end up damaging themselves. So it is often really a good idea to put a resistor in the circuit with an LED. And so it's a current limiting resistor. And it also helps you get the LED to that specified forward voltage that's usually on these data sheets. Now, if this sounds complicated, don't worry too much about it because there are a lot of great tools online for how to calculate the value of these resistors, and we're going to go through that right now. All right, so to get started here, let's go to Adafruit, and we'll look up our little LED. So tricolor, and that's our diffused RGB, excellent. So Adafruit is going to give us all of the information that we need here, which is the forward voltage for each color of the LED. So if we zoom in here, you can see that red is 2.1 to 2.5 volts at a 20 milliamp current. Green is 3.8 to 4.5, and blue is 3.8 to 4.5. Now, our processor operates at a logic level of 3.3 volts, so we won't be able to provide exactly that forward voltage, but that's still okay, and we can plug that into our resistor calculator to figure that out. So let's go ahead and open a new tab, and we'll do an LED resistor calculator. There are a ton of these online. I'm just gonna click the first one, and we're gonna use that. So our source voltage for these LEDs is going to be 3.3 volts. Now the voltage drop is the forward voltage that is listed here. So let's do the red LED first. So the voltage drop here is going to be 2.5 volts. That's what we're gonna drive it at. So here we go, 2.5. And the current through the LED, we need to be sending 20 milliamps through the LED. Now our processor can send that amount, so it's all okay. I'm gonna say 20 right here. And we're gonna calculate. Here we go. So we need a 40 ohm resistor right here in our circuit. I'm gonna go back to my schematic. We're gonna copy this resistor right here. Oh, can't. I need to turn that off. Okay, and we're just gonna put that up by the red. We're gonna put a 40 ohm resistor. I'm actually gonna move these around a little bit, just so it's a little cleaner. So let's move this up here. And we're going to rename the value of this to be 40 ohms. Okay, now let's do the blue LED. So the blue LED operates at 3.8 to 4.5 volts. But the source voltage, let's see if this works. The source voltage is still 3.8, but let's see if this works at 4.5 volts. Yeah, it doesn't work. So we're actually going to just operate this at 3.3 volts, calculate, and we don't technically need a resistor there, but I'm going to go ahead and put a 1 ohm resistor anyway, just because we want to limit some of the current in that circuit. So we're going to go ahead and copy this guy. Here we go. And I'm going to change the value of this to, oops, here we go, 1 ohm. Excellent. And I kind of have a feeling that's going to be the same for the green LED, which has a forward voltage of 3.8 to 4.5, which means, yep, 3.3 volts, because that's the maximum we can send from our processor. So it's going to be a 1 ohm resistor on that one too. We're going to go ahead and copy that. And excellent. So we have a 1 ohm resistor, and a 40 ohm resistor. We're going to connect these up to the actual LED. So here we go. 1, 2, and 3. Okay, so next we're going to break out each one of these resistors, and these are going to be the pins that control the actual LEDs themselves. These are going to be connected to the GPIO ports on the processor. So we're going to label these NS5, NS6, NS7, and we're going to rename them, predictably, to red, let's see, LED red, LED blue, and LED GRN for green. Excellent. Now, here's the thing. This is a common anode LED. It's not a common cathode, and the anode is basically the positive. So we're actually going to be feeding 3.3 volts into this side, and then the GPIO pins are going to drive the LEDs low when it's time to turn them on. It's a little counterintuitive, but it should work just fine. Now we're going to use the 3.3 volt line coming out of the Teensy processor. So that's going to be our positive voltage here. We're going to create a little label, and we're going to connect that net. Here we go, 3.3V, enter, yes, and now our LED is connected up, except we need to connect to the GPIO pins, so it's time to pick some digital pins on this processor to use. I'm going to pick pins 14, 15, and 16 here to control our RGB LED. So let's put some labels on here. And the reason I picked these is mostly what I'm trying to do is avoid using any of the PWM pins, because that's going to be necessary, or those pins will be necessary to use for the servo and for the buzzer. So let's go ahead and name these. That's LED red. This one's LED BLU. And this one is LED GRN. Excellent. These are now connected. Okay, now we should probably take care of the Pyro channels. I'm not going to get too detailed into the reasoning behind this circuitry, but I am going to sort of explain it for at least one of these channels. So we need 2 resistors per channel. One resistor will be a current limiting resistor, so we're going to put this at just 1 ohm. And then the other one is a pull-down resistor, and that's going to be just 470 ohms. And the pull-down resistor is basically going to make the whole Pyro channel situation a lot safer. The pull-down resistor ensures that no matter what, so long as we do not send a very intentional high signal to the Pyro channel, it will be off, or it will be an open circuit, which basically means we're not going to fire anything on the computer unless we really intend to. Okay, so let's wire these things up. This guy's gonna go right here, draw a line from here to here, and then we need a power source here too. So we're actually going to be sourcing this directly from the battery, and that's that 12 volts that we set up earlier. So I'm gonna go ahead and break this guy out, and I'm gonna call this, let me put a label on there, and I'm gonna call this 12 volts. Excellent. So the current is going to come from the 12 volts. It's going to go through whatever is connected to this Pyro channel. It's going to come out. It's going to go through a small current limiting resistor. Then that current limiting resistor goes into the MOSFET, and then coming out of the MOSFET, it goes into ground. So let's go ahead and copy another ground part right here. And we're going to put that down here. There we go. MOSFET goes into ground, and then we need that pull down too, so that the MOSFET stays off as long as we want it to. So we'll connect this to ground, we'll connect this part to the resistor here, and then eventually this lead will connect to the GPIO pin that actually controls this Pyro channel. But before we do that, I have a better idea about how this should work. So instead of just redrawing the circuit for every single one of these, what I'm going to do is I'm going to take the selection tool, which I can find right here, the group tool, and take that, and I'm going to delete those. I'm going to take this tool, I'm going to select this whole thing, then I'm going to use the copy tool. I'm going to say copy group. We're going to put 1 there. We're going to do another copy group, 1, 2, and then we're going to do another copy group right here, 3 and 4. Excellent. So these are our 4 MOSFET channels. These are our 4 Pyro channels. They each need to be connected up to 1 GPIO pin, and there are 4 right here that are just they're just waiting for it. So let's hook those up. 1, 2, 3, 4, and then we're going to label these pins too. So we're going to put little labels on them, just like everything else that we've done so far. 1, 2, 3, 4, and then we're going to name them. So here we go: PY1, PY2, PY3, and you guessed it, PY4. And then we have to take these and connect these leads too. So we're going to draw leads out from here. We are almost there, folks. sit tight. 3, oops, that's too long. 3, kind of want them to match too. And 4, and this one is like a little bit out of line, and I just want to fix it. So we're gonna do this, move group, excellent. Now that is in line. So then we're gonna take these, we're gonna label them 1, 2, 3, 4, and then we're gonna take the naming tool, here we go, PY1, connect. PY2, connect. Then we're gonna say PY3, connect. And finally, once again, PY4, connect. Okay, our Pyro channels are wired and connected. This is such great news. Let's do something easy now. How about the buzzer? Okay, so let's move this around a little bit. I'm gonna move this buzzer up here. I'm gonna move the LED down a little bit too. We're just kind of trying to make this look really nice. So we'll move group, and that's going down there. Okay, so for this buzzer, we're just gonna draw 2 leads out of this. We've got 1 and 2. And one of these is going to be the input, one of these is going to be ground. And actually, as I think about it now, we should have only drawn 1 lead. It's going to be that's going to be the input, and the other one is going to ground. So we're gonna take our copy tool, once again, our favorite friend in this little program, and we're gonna send this part of the buzzer to ground, and the other part we're going to label as, here we go, buzzer, boom, done. Now, this buzzer pin is going to go on a PWM pin. That's a pulse width modulation, and that's what's going to let us do a little bit more fancy stuff in terms of different tones on the buzzer. So we're gonna pick pin number 10 here. I'm gonna go ahead and label this, and I'm gonna connect it to the buzzer net, buzzer, and connect. Excellent, so our buzzer is connected. That was really fast. One of the other helpful things that we can add to this computer is a little voltage detection circuitry so that we know the voltage of our battery. This is going to help keep our flight safer so that if our battery is too low, our computer can warn us. So let's go ahead and break out pin number 17 here, or analog pin 3. I'm going to go ahead and label this as, let's see, what should we label this as? How about how about just voltage? And this is going to tell us how many volts our battery has. But how are we going to figure this out? Well, we're going to use something called a voltage divider. Now, a voltage divider is just a little circuit that uses 2 different resistors in it. So we're going to use one here and one here. And basically, the way that this works is we have a lead coming from here going to this first resistor. And this lead is going to be our 12 volt signal. So let's go ahead and label that right here. We're going to name this 12 volts. Yep, we're going to connect them. Then we're going to have this go down to this second resistor. And this second resistor is going to be a little bit smaller than the first. And the second one is going to go out from here into ground. So let's go ahead and copy this right here into ground, and excellent. Now, what happens in between these is why it's called a voltage divider. So we're going to break this part out, and we're going to call this part voltage. This is the actual pin that's going to go into the computer. So I'm going to rename this voltage. Excellent, it's connected, and these values of the resistors need to change. The first one is going to be, yep, here we want to change it, 1 or 1 mega ohm, and the second one is going to be 100 k ohm, or 100 kilo ohms. And I chose these values before. I'm not going to go into the details of why, but these are good values for the battery sizes that we're going to be using and the tolerance of the processor. So anyway, this is our voltage divider circuit to help us detect our battery's voltage. All right, so our computer is looking pretty good, but I kind of feel like we might be forgetting something. Does anyone know what we're forgetting? It's the most important part of this. It's thrust vector control. We didn't add any servos to this thing. So let's go into our parts selector here, and I'm just going to search for servo because there's a bunch of things that are just pre-made for this. So here we go. Look, it even draws a little servo for us. I'm gonna put this up top, 1 and 2, because we only need 2 thrust vector control servos for this. Each one of these has a black wire, a red wire, and a white wire. So the black wire is going to go to ground. We're gonna do another one of these little copy-paste things with the ground signal here. Here we go. This black is gonna go to ground, and we're also gonna do the same for this servo. And let's go ahead and wire that up. Black to ground, black to ground. Excellent. Now the red is going to go to 5 volts because that's how much we're going to be sending to the servo. And once again, the 5 volts actually has its own little symbol. So we're gonna go ahead and copy this 5 volt signal right here. I'm gonna put it under there and one for the other servo as well. Then we have to connect them up. 1 and 2. Okay, and the white is the actual, this is the most important part. This is the signal that is coming from the processor. And so we're gonna do 1 and 2. So now we're gonna label these. These are going to be, get ready for it, TVCX and TVCY. And now we have to connect these on the processor, and we want, I mentioned this earlier, but we want PWM pins, or pulse width modulation. And that is basically the way that the processor communicates to the servo to tell it which direction to point. So we're gonna break these out of 3 and 4 here because they both say PWM. So here we go, 1 and 2. And I'm gonna label these again. 90% of this tutorial is just me labeling things. So we're going to go ahead and rename these TVCX, connect them, and TVCY, connect them. Okay, we are so close to done, folks. We have just one more thing to do, and it's that I wanna break out a bunch of extra pins so that if people are using this and they wanna experiment, they can just use the other pins, or they can connect other things to here. So let's add some header pins onto this computer. Okay, and to do this, we're just going to use a standard header pin, and I want 10 pins total to be broken out. So I'm gonna go into the parts list here, and I'm just gonna search for header. Here we go. And I want it to be a 5x2 pin. So this is kind of how it's going to look. Let's see, which one looks good to me? I'm thinking 5x2, and I don't think we need any silkscreen on it too. So this is just standard spacing, 5x2 header pins. It's gonna be a little block on the computer that looks like a little, kind of looks like a little caterpillar. We're gonna put this here, and I'm just gonna break out all of these pins and add a bunch of extra functionality so that if folks wanna mess around and do their own kind of rocket computer, they can do that too. So we're gonna break this out. 1, 2, 3, 4, 5. And then the same on the other side. 1, 2, 3, 4, 5. Okay, and Joe, what do these pins do? What a great question. So we're just gonna break out these 1, 2, 3, 4, 5 here. So here we go, 1, 2, 3, 4, 5, and it doesn't even matter what you do with them. This is the best part, is you can choose whatever you want to do with these pins. You could use them as extra chip selects. You could use them as, I don't know, put more buzzers or more LEDs on your rocket, whatever you want. So here we go. We're just going to call this header 1. Oops. Header 2. Header 3. Oops. Header 4. And header 5. Excellent. So now, predictably, we're going to just go ahead and relabel these. 1, 2, 3, 4, 5. And we're going to do the same thing. Header 1. Oh my gosh. Header 2. Ah, that's header 23. Header 2. Yep. Header 3. I'm losing steam. Header 4. And header 5. Excellent. So now the other 5 pins on here are going to be a little bit different. These are less customizable pins, but they do continue to add more functionality to this computer. So the first 2 here, we're going to do the top one. The top one is going to be, let's see, I think this should be 5 volts. So let's actually delete the thing here so that we can connect that little 5 volt pin to it. So we're going to go ahead and do this. And I'll connect that to 5 volts. And then I will connect this to ground. And there we go, so that when you break out something and you put an extra sensor or something like that on here, you basically want to be able to have a common ground and a common 5 volt line. So let's go ahead and label these guys right here. So 1, 2, 3, and what I'm going to do is I'm going to break out the SPI lines. So the SPI lines again are SCK, MISO, and MOSI. So here we go. If you wanted to add more sensors or more things like that, you could do so through the SPI bus. And here we go. So MISO, we're going to connect those. MOSI, connect those, and SCK. Excellent. And you know, as I think about it more, it would be great to add the SCL and SDA lines. That's the I2C lines. And you know what? The cleanest way that we can do this is we get rid of all of the headers and redo them again. We're going to get rid of these and then just start clean. So header 1, 2, I'm kind of like live designing this, but here we go. Header 1, header 2, and header 3. Let's go ahead and label these. Header 2 and header 3. Excellent. Okay, so we have 3 GPIO that we can break out, and then the other 2 here are going to be the SCL and SDA lines. So that's the I2C. And again, that's just going to enable a lot more flexibility down the road for people who want to modify this stuff and build their own version of it or their own flavors. So SCL and SDA. Okay, now header 1, 2, and 3, we have to reconnect those. Header 1 is connected. So we're going to do 2 and 3 on the RX and TX lines, so that if you wanted to connect something to a serial port, you could do that as well. We're just trying to break out all of those ports. So let's go header 2 and header 3. Okay. Woo! So that's it. This is the Blip computer schematic, and it's all complete. Now, is everyone ready to do the same exact thing for Blop? Because here's the thing. I don't want this video to be 3 billion hours long, so we're going to use the same concepts for Blop, but instead I'm going to be time-lapsing through it and explaining just the differences and why there are small changes between the Blip and Blop flight computers. So, are we ready? Here we go. 3, 2, 1... time lapse. So for Blop, the processor is going to be mounted directly on the main PCB instead of on the Teensy board for this computer. So we're going to need to replicate most of the circuitry that Paul from PJRC has really generously published on his website. The only consideration here is that we'll need to purchase a custom bootloader chip directly from PJRC, but that's a very small price to pay for the easy implementation of the Arduino environment on this awesome processor. As a heads up, I'm also speccing all of the components on this board to be the 0805 size, so it shouldn't be too hard to hand solder them yourself. We also need to replicate the sensor breakout circuitry, so there are a few extra filtering capacitors near both the barometer and the IMU. Plus, we'll need some pull-up resistors on those I2C lines. I've kept the pin mapping identical between these computers, and so during the layout phase, if anything is changed on one computer, it'll be changed on both. This way, if you start out by working on one computer and you want to switch over to the other, the software will be the same. And so with that, the Blop schematics are all set. Now, again, this is not a fully fledged tutorial. I'm still trying to bridge the gap between being informative and moving fast enough to stay entertaining. I am also by no means an expert in this field. I'm just a guy who learned these things through trial and error, reading forum posts, and watching a bunch of YouTube tutorials. And speaking of which, once again, those YouTube tutorials that I used and that I think might be helpful are linked in the description down below. Right now, I'm pretty happy with both of these schematics, but we won't actually know if they work until we get the layout done and these boards built and tested. And of course, if something doesn't work or it needs to be changed or I just want to make modifications, I'll push those updates to the files which are available on Patreon. In the next episode of Landing Model Rockets, we're going to be designing the layout for both of these boards, and this is the physical placement of the components on these PCBs. It's worth mentioning that sometimes during the layout phase, there are schematic changes that have to retroactively happen. This usually isn't any major circuitry, it's just a couple of GPIO changes so that things are more convenient for the processor or for the routing. And as mentioned before, if those changes are made, I'll update the files on Patreon. That said, if you want to download these files to modify them for your own PCB or your own board, this is probably the time to do it, because we're going to be moving forward with this design, which will be more locked in as time goes along. So if you want to do that, the files are linked down below, and that's it. So thank you so much for watching. My name is Joe Barnard. May your skies be blue and your winds be low.